Welcome to the Center for Energy Education's online video series on energy storage. My name is Jason Bone and I teach the photovoltaic or solar program at Halifax Community College. Over the next couple of weeks, we're going to look at electrical energy and how and why we need energy storage. A watt not consumed is a watt that does not have to be generated, processed, or stored. For this very reason, we're going to start this series discussing conservation and efficiency. Let's begin our discussion by taking a look at where our energy comes from. This will help us in understanding why energy storage is of concern. The majority of our energy production, roughly 74%, comes from non-renewable sources or fossil fuels. These dwindling fuels are actually stored energy in and of themselves, but because there is a finite supply and greenhouse gases emitted from the releasing of this stored energy, we need to look elsewhere for a cleaner, sustainable energy source. We will talk about the process of turning these energy sources into electricity in another lesson. The remainder of our energy pie are renewable or sustainable sources of energy. These offer a cleaner outlook for us and future generations. As we alluded to earlier, it's much more cost-effective to conserve energy than to generate energy. So let's explore that idea today. For the homeowner, the biggest savings on energy can be accomplished by concentrating on the largest energy consumers in the home: space heating, cooling, and water heating. While these items are not cheap upgrades, simple things like washing clothes in cold water, sealing cracks and gaps around windows and doors, keeping heating and cooling system filters cleaned or changed on a regular basis can go a long way in the efforts of conserving energy and saving money. Keep in mind, the most efficient appliances, lights, or electronic devices are the ones that are turned off when not in use. When shopping for energy-efficient upgrades, keep an eye out for the Energy Star certification logo. I would recommend visiting www.energystar.gov whenever you're looking to upgrade any appliance, lighting, or electronics in your home. Energy Star is the government-backed symbol for energy efficiency, providing simple, credible, and unbiased information that consumers and businesses rely on to make well-informed decisions. Since 1992, Energy Star has helped American families and businesses save more than 4 trillion kilowatt-hours of electricity and achieve over 3.5 billion metric tons of greenhouse gas reductions, the equivalent to the annual emissions of more than 750 million cars. In 2018 alone, Energy Star and its partners helped Americans avoid $35 billion in energy costs. In addition to major appliances, Energy Star also certifies building products, commercial food service equipment, data center equipment, electronics, heating and cooling equipment, lighting, office equipment, and water heaters. On their website, you can also find information on federal income tax credits and other incentives for energy efficiency. No discussion on energy conservation can be had without talking about phantom loads. What is a phantom load? A phantom load is an electronic device that consumes electricity while it is turned off or in a standby mode. A few examples of phantom loads are desktop computers and displays, satellite and cable boxes, printers, stereos, televisions, microwaves, video game consoles, and phone and laptop chargers. Once our phones or laptops are charged, if these charging devices are left plugged into an electrical outlet, they still consume and waste energy. Some phantom loads, such as wireless routers and internet modems, are never turned off. These devices consume energy 24 hours a day. A few strategies we can use to try and minimize this wasted energy is to use Energy Star certified appliances, plug these devices such as televisions, cable boxes, and routers into power strips that can be turned off to ensure no current draw when not in use. Unplug phone and laptop chargers from the devices as well as the electrical outlet upon reaching full charge. I measured the current draw of my MacBook charger when it wasn't connected to my computer. It measured 9.2 milliamps of current. Let's calculate the energy wasted by leaving it plugged in all day. Power is equal to current times voltage. 9.2 milliamps, or 0.0092 amps, times 120 volts is equal to 1.104 watts. And the watt is an instantaneous value of electrical energy production, or in this case, consumption. To find energy, we simply add a time component, typically in hours. If my charger was left plugged in for 24 hours, it would consume and waste 1.104 watts times 24 hours equals 26.5 watt hours per day. Over the course of a year, that would equate to 26.5 watt hours per day times 365 days for a total of 9,670 or 9.67 kilowatt hours per year of wasted energy, all off one device. Phantom power accounts for more than 100 billion kilowatt hours of annual U.S. electricity consumption and more than 10 billion in annual energy costs. This is energy that we are generating, consuming, but not using, and money we are throwing away. Lighting is another area where we can save on energy. When it comes to light bulbs and brightness, we're used to thinking in wattage. But wattage doesn't tell us how bright a bulb is, it tells us how much energy it consumes to create that light. Lumens will help us determine the brightness of a bulb and help us navigate the newer options in light bulb technologies. The three main types of bulbs sold today are the traditional incandescent bulb, the CFL or compact fluorescent bulb, and the LED or light-emitting diode bulb. Here we see three bulbs that are all equal in light output, 1600 lumens, but very different in the amount of energy they use. Let's explore these three options and see how much energy each consumes throughout the course of a year. Imagine a ceiling lamp in your living room that holds four 100-watt incandescent bulbs. How much energy would it consume if it was turned on for 4 hours a night? The total power would simply be the number of bulbs times the wattage of each bulbs, or in this case, 4 bulbs times 100 watts for a total of 400 watts. The total energy consumed would be 400 watts times 4 hours a night, which would be 1,600 watt hours per day, or 1.6 kilowatt hours per day, for a total of 584 kilowatt hours annually at a cost of approximately $58.40. Let's examine how these numbers change as we swap out these 4 incandescent bulbs to more efficient CFL bulbs. Starting with our total power, again we take the number of bulbs times their wattage, or in our case 4 bulbs times 23 watts each, for a total of 92 watts. As we see, these 4 CFL bulbs require less power than one of the incandescent bulbs from our previous calculation. Looking at the total energy consumed, we have 92 watts times 4 hours per evening for a total of 368 watt hours, or 134 kilowatt hours annually at an approximate cost of $13.40. CFL bulbs do come with a few disadvantages, as they take several minutes to achieve full brightness, and due to a small amount of mercury, require special attention when being disposed of. The EPA recommends that you bring old CFLs to qualified recyclers rather than disposing of them in trash cans or curbside recycling bins. Old CFL bulbs can be taken to the Home Depot and/or Lowe's Home Improvement for free recycling. And finally, let's replace these 4 CFL bulbs with even more efficient LED bulbs. As in our previous examples, our total power is equal to the number of bulbs times each bulb's wattage, or in this case, 4 bulbs times 14 watts each, for a total of 56 watts. The total energy consumed for 4 hours per night would be 56 watts times 4 hours for a total of 224 watt hours, or 82 kilowatt hours annually at a cost of $8.20. Let's take a minute to examine the Energy Star label found on their certified bulbs. They start off with the most important concern for a bulb, brightness. As seen here, 800 lumens. The next section tells you the estimated yearly energy cost based on 3 hours of use per day. Life is next on the list, and something we have yet to mention. Traditional incandescent bulbs typically last 1.5 to 2 years. Here we see a life of 22.8 years on an Energy Star certified LED bulb. Keep this in mind as you shop for LED bulbs. While they cost a bit more up front, they pay off greatly in energy savings and bulb life. Life is followed up with light appearance and is an important consideration. Traditional incandescent bulbs produce a warm white light with a color temperature in the 2700 to 3000 degrees Kelvin range. Bulbs listed with a color temperature in the 4000 to 6500 degree Kelvin range will produce a cooler bluish light. Most buyers prefer the warmer 2700 to 3000 Kelvin range. And finally, energy used or bulb wattage is listed. In the case of the CFL bulbs, as seen here, an additional piece of data is given. This is the warning of an extremely low level of mercury, as we've mentioned earlier. Here we see a chart that may assist you in making decisions as you move into purchasing more energy-efficient bulbs. The first column lists the most common bulb wattages used with traditional incandescent bulbs: 100, 75, 60, and 40 watts, followed by their lumens output in the next column. Instead of purchasing by wattage, start thinking lumens to match light output. I think it's pretty clear from our earlier discussions, LEDs now reign king of the bulbs. Before we end our lesson on conserving energy, let's look at another area where LEDs are greatly reducing energy consumption and saving communities vast amounts of money at the same time: the traffic light. How many are in your city, town, or community? The fact is, most intersections have more than one traffic light controlling the flow of traffic. If you think about it, even the most simplest of traffic lights has 4 bulbs on at any one time, and they are on for 24 hours a day, 365 days a year. Just think of how much stress can be removed from our power grid and how many tons of greenhouse gases we can eliminate by simply changing to LED bulbs, not to mention the money and man-hours saved due to less maintenance from the increased lifespan and improved efficiency. Let's look at a simple traffic light using the traditional 100-watt incandescent bulbs. Remembering that 4 bulbs will be on at all times, how much energy is being consumed? 4 100-watt bulbs on for 24 hours consumes 4 bulbs times 100 watts per bulb times 24 hours a day will be a total of 9.6 kilowatt hours of energy per day. If we multiply that daily consumption value by 365, we get 3,504 kilowatt hours of energy per year. If using 14-watt LED bulbs, 4 14-watt bulbs on for 24 hours consumes 4 bulbs times 14 watts per bulb times 24 hours a day equals 1,344 watt hours, or 1.344 kilowatt hours of energy per day. That's only 490 kilowatt hours of energy per year, or a savings of 3,014 kilowatt hours of energy from one traffic light. I know many of these examples we discussed seem like small numbers, but when you think about the fact that there are 3 million households in North Carolina alone, small changes can have huge consequences. As we saw earlier, using 4 incandescent bulbs 4 hours per night for 1 year consumes 584 kilowatt hours of energy annually. Multiply that by 3 million and we are consuming 1.8 billion kilowatt hours of energy per year to power 4 bulbs 4 hours a night in each home in North Carolina. If these bulbs were changed out to LEDs, which only consume 82 kilowatt hours of energy annually to make the same amount of light, how much energy could we conserve? 1.5 billion kilowatt hours of energy every year. Little things like this become big things when we start looking into storing energy. I think you can see from this example that by simply changing out 4 light bulbs in every home in the state of North Carolina, the amount of energy we would need to store would be greatly reduced. I hope you enjoyed our discussion and gained a little insight into how you doing small things helps us as a community do big things.